This is problem 104 from chapter 15. In problem 104, a 4-pound ball B is traveling around in a circle of radius 3 feet with a speed of 6 feet per second. If the attached cord is pulled down through the hole with a constant speed of 2 feet per second, determine how much time is required for the ball to reach a speed of 12 feet per second. How far is the ball from the hole when this occurs? Neglect friction and the size of the ball. So first, let's do a free body diagram for this situation. So we have our ball here, and we have the normal force acting upward. We have the force of gravity acting downwards. Let's call this the z direction. There's no acceleration in the z direction, and the ball is staying at the same height, so these forces must balance. So the net force in the z direction is equal to 0. Then we have the cord here, which is exerting a force on the ball. I'm going to call that force F. Okay, so and we have no friction, so those are the only forces that we have acting on the ball. We want to find the time that it takes to reach a speed of 12 feet per second. So initially the ball is going in a circle, but then when you pull the cord, you're going to have a component of the velocity sometime later when the ball reaches a radius of r2, you're going to have a component of the velocity in towards the center of the circle and also in the transverse direction. So let's call this v b theta at event 2, and this is the radial component, but it is pointing in towards the center of the circle, so in the negative r direction. So using cylindrical coordinates, we have the transverse direction and the radial direction, which is pointing outward, and the z direction, which is pointing upward. They tell me to find the time when the speed of the ball is 12 feet per second. The speed of the ball, v b2, is equal to 12, but that is the radial component squared plus the transverse component squared. This is at event 2, and it's squared. So I know what this is because VR is equal to 2 feet per second. So if you're pulling on the cord with 2 feet per second, you're going to have this component being equal to 2, but it's in the negative r direction. So this is equal to negative 2 because that's the speed of the cord. So I can take this equation and solve it for the transverse component. That would be the square root of, so you can square both sides and you get 12 squared on this side. Then subtract this, that's 2, so minus negative 2 squared. And that gives me 11.83. And if the ball is going around this way, that would be in the positive transverse direction. And this would be feet per second. So we have the transverse component and the radial component. Now I'm going to go to my equation for this section, which says that the initial angular momentum plus the sum of the moments integrated with respect to t is equal to the final angular momentum. So I need to say what the initial angular momentum is and what the final angular momentum is. Now, for the initial angular momentum, I'm using equation 1513, and I can go ahead and put that right into equation 1518. So initially, I'm at position 1. We could call that vector R1, and remember that's going from the origin to the object. So that would be, let's say, if the object starts off over here, this would be R1 crossed with the mass times the initial velocity. That would be the VB1. The object was going around in a circle to begin with, so initially that velocity is just in the transverse direction. That's perpendicular to my r1 vector. Okay, then plus the sum of the moments integrated with respect to t, that comes from this equation here. That's the vector r crossed with the net force acting on your object. So let's say plus the vector r crossed with F net and integrated with respect to t. But up here, we said that the net force in the z direction is equal to 0. And so we just have the force of the chord acting on the object. But at any point that you look, so either here or anywhere along the way up until we get to event 2, r is pointing from the origin to the object, and this force of the chord is pointing in the opposite direction. So for the cross product here, you're always going to get 0 because whatever direction r is pointing in, F is pointing in the opposite direction. So then we have the final angular momentum, which is the vector r2, which is pointing from the origin to the object. That's our vector r2, crossed with m times v b2. When we do this cross product, the radial component of the velocity is going to give us 0 when we do r crossed with the velocity vector. We're not really familiar with doing cross products with cylindrical components. We could write this using rectangular coordinates instead. So at event 2, my vector r2, let's say, has a magnitude of r2 and is pointing in the I hat direction. My velocity at event 2, the radial component is pointing in the negative I hat direction, so that would be VBR at event 2 in the negative I hat direction, plus this component, which at event 2 is pointing in the J hat direction, just because I happen to pick event 2 to be there, but it doesn't really matter where it is. So this is VB, this is the transverse component at event 2 in the J hat direction. So when I do this cross product here, I'll have an I hat crossed with an I hat, which gives me 0, and an I hat crossed with a J hat. I hat crossed with J hat gives me K hat. But you don't have to write it in rectangular coordinates, but it may help you to see what's going on there. So it's only the transverse component which is going to contribute to the cross product here. So if we didn't write it out with the unit vectors here, we would say, because the angle between my position vector here and my transverse component of the velocity is a right angle, then it would be the magnitude of r2, which is what I'm looking for, so let's just call it r2, times the mass, times the transverse component, and then you could say times sine of the angle between them, which is 90 degrees, so that would give you 1. And if you use the right hand rule, r is going this way, the transverse component's going that way, so that would be in the K hat direction. And the radial component, again, gives you 0 because the vectors are pointing in the opposite direction. So you'd have sine of 180 degrees when you do the cross product for this component. So that would give you 0. Then we still need to take care of this cross product. So R1's going this way, VB1's going that way. That's also pointing in the K hat direction. We have the magnitude of R1, which is 3 feet. We have the mass, I'm just going to leave that as m because that's going to cancel out with what we have over here. The magnitude of my velocity vector at event 1 is 6 feet per second, and this we said is pointing in the K hat direction. Okay, so the mass cancels out. I'm looking for the time it takes to reach 12 feet per second and R2. Oh, I know what this is. That's 11.83. So I can take that and put it in there, and then I can at least find R2. There's a k-hat on both sides, so I can just write this as R2 is equal to 3 feet times 6 feet per second. That would be 18 feet squared per second divided by 11.83 feet per second, and that gives us 1.52 feet. This is R2, which we were asked to find, but we were first asked to find the time it takes to reach 12 feet per second. So now I have to go back and do that. So if I'm looking in the radial direction, the speed in the radial direction is constant because the rope is being pulled at a constant speed. So I can say the radial component for the ball here that's pointing inward, so let's make that negative 2 feet per second. So they said VR is 2 feet per second here, but that was the speed of the cord. Since it's pointing in towards the circle, towards the center of the circle, I'm going to make it negative for the ball. So that's the radial velocity of the ball. It's constant. And because it's constant, I can say a constant velocity is equal to delta R over delta T. So I ended with R2 being 1.52 feet. So I'm going to do R2 minus R1 over delta T. That's 1.52 feet minus, we started at 3 feet, divided by the time. Oh, the time is what I'm looking for. So that's just delta T. This is equal to negative 2 feet per second. So in the numerator here, I have negative 1.48 feet. And over here I have negative 2 feet per second. So delta T is equal to 1.48 feet divided by 2 feet per second. And that gives me 0.739 seconds. And that is my solution for problem 104.